In this lecture, we're going to go over isentropic processes, in particular for ideal gases. So an isentropic process is one that occurs at constant entropy. If two states have the same specific entropy, our equation reduces down to 0 is equal to S naught at T2 minus S naught of T1 minus R times the natural log of P2 over P1. For example, if we know the temperature at state 1 and the pressure ratio, we can find the temperature at state 2 by solving the equation for S naught of T2. The temperature and pressure at state 1 were known, and the temperature at state 2, we could find the pressure at state 2 by rearranging the equation to get P2 is P1 times the exponential of S naught of T2 minus S naught of T1 over R. If we know our S naught data, solving these equations for state 2 is very simple. There's a very special case for air and air only. I can express the ratios of my pressures as P2 over P1 is equal to the exponential of the S naught of T2 over R over the exponential of S naught of T1 over R. Since our exponential is only a function of temperature, we give it a new symbol P sub R of T, which gives us the relationship that P2 over P1 is P equal to PR2 over PR1. This is only valid for constant entropy and air only. The PRs are tabulated in our table for air. We can develop a similar relationship for our specific volumes. Again, since the states have the same specific entropy, I can use my PR relationship for my pressure relationship. We define the ratio of RT over PR as a variable V. So you get V of 2 is equal to VR2 over VR1. And again, this is only for constant entropy and air only. The VR values only appear in A22 for air. If we assume constant specific heats, our entropy balance using constant specific heats reduced down to 0. It's equal to Cp times the natural log of T2 over T1 minus R times the natural log of P2 over P1. And 0 equals Cv times the natural log of T2 over T1 plus R times the natural log of V2 over V1. If we recall our ideal gas relationships, that Cp is equal to Kr over K minus 1, where K is our specific heat ratio. We also have Cv is R over K minus 1. We can solve these above equations and get that T2 over T1 is equal to P2 over P1 to the K minus 1 over K. And T2 over T1 is equal to V1 over V2 to the K minus 1. Again, this is for constant entropy and constant specific heat. We can eliminate temperature from these relationships to get P2 over P1 is equal to V1 over V2 to the K. For an ideal gas with constant specific heat ratios, a polytropic process, that is PV to the K, is an isentropic process. Let's look at an example. We have air undergoing an isentropic process from 1 atm and 540 degrees Rankine to a final state where the temperature is 1160 degrees Rankine. Employing the ideal gas model, we want to determine the final pressure. We're going to solve this problem using the PR data and using a constant specific heat ratio that's evaluated at 850 Kelvin. So for the PR data, we know that P2 over P1 is equal to PR2 over PR1. If I solve for P2, I get P2 equals P1 times PR2 over PR1. So if I go to table A22E, at the temperatures I'm given, PR1 is 1.3860 and PR2 is 21.18. So you get P2 is equal to 1 atm times 21.18 divided by 1.3860, which tells me that P2 is equal to 15.28 atm. So if we use constant specific heats, we know that P2 is equal to P1 times T2 over T1 to the K over K minus 1. To get our K, we're going to go to table A20, and at 850 degrees Rankine, K is equal to 1.39. So P2 is 1 atm times 1160 over 540. It's the 1.39 over 1 minus 1.39. Nope. 1.39 minus 1, which gives us 15.26 atm. So those are the two ways you can evaluate isentropic processes for ideal gases. In our next lecture, we're going to go over the isentropic efficiencies of turbines.